In this module, which will be the most basic module we will be discussing, we will be looking at how the computer system works at the lowest level. That is a bit. How bits combine together and become larger numbers, binary numbers. How these bits are put together into logical operations. How they combine into AND, OR, XOR gates. How they are represented as hex numbers. And then how mathematical computation is done with these bits with unsigned and signed integers. This forms the basis of how complex operations are done in a computer, so it's good to understand the bit and the data system at this level.
Okay, so a single bit is actually very powerful. A single bit's state of 0 represents off, a state of 1 represents on. A state of 0 can be considered a false and a state of 1 can be considered true. In itself, it's very powerful to build a state system. But what else can you do with a bit? Well, if we get two bits together, we can build logic operations. And these are the fundamental building blocks of a computer system. There is AND, OR, XOR, and NOT. An AND logic system will take two inputs, 2 bits, and produce 1 bit as an output. So an AND says that if only both of the bits are 1, the output can be 1. An OR logic says that if any of the input bits are 1, the output will be 1. The XOR logic will say that either of the bits can be 1 and then the output can be 1, but if both are 1, then the output is 0. A NOT is a simple operation on a single bit, which means that if it is true, it becomes false. If it is false, it becomes true. So these are the basic logic operations. Computer systems also then expand on the basic logic operations and build those circuits together from logic operations into arithmetic units. A basic arithmetic unit will be one that adds two numbers. So if you have input 1 and input 2, they add up and then you get a result. So 0 plus 0 is 0, 0 plus 1 will be 1, 1 plus 0 is 1. Now when you add 1 and 1, the problem is the result is actually 2, but we only have 1 bit to store the result. So the result becomes 0, but there is a carry. Now the carry is how larger numbers are built together, but in this case, this result is 0, the bit sets to 0 and then sets a carry flag. So what could we do if we really wanted to work with bigger numbers? Because with a single digit, you can actually work with just 0 or 1. You can add them up as 2 bits, and then you can work with 0 to 3. And with 2 bits, you increase the exponent. And this is just like the decimal system. The binary system works on an exponent to 2. So the first digit becomes a 0 exponent to 2. So 2 to the power of 0, you can represent 1. With the second digit, you represent 2 to the power of 1, so the number 2. So if we use now 2 bits, we are able to go beyond just being able to represent 1. We can now use 2 bits, and 0 will represent 0 in decimal. 0, 1 is still 1. But now we are able to represent 1 and 0. So the second bit that we have represents a 2. But we also can add 1 and 1 with these 2 bits and represent a bigger number, which is 3. So a similar model is used to expand on the number of digits we use. A 4-bit number range will be even bigger than a 2-bit number range. So 4 bits can give you from 0 to 15. And in a very similar model, this table represents here how you're able to put 4 bits together and how you can change the value of each bit, and an increasing bit will be an exponent higher. So as we added 4 bits, the third bit is 2 to the power of 2, it will represent a 4, and the fourth bit will be 2 to the power of 3, so it will represent an 8. So pretty much to find out the number, you get each bit's value and add it up, and that's the value in the decimal system. You can go beyond 4 bits and you can show 8 bits. And that's an even bigger number range. It goes to 255. You can use 16 bits, and then you get an even bigger number range of numbers, and you can go from 0 to 65,535. Just look at the number of ones that are increasing here. So if you keep on increasing the length of ones, it becomes really hard to note these numbers down. So there is then the hex representation, which is used in computer systems. What hex does is it helps you compress the bits into a smaller number of numbers or digits that you have to show those larger number of bits in. So the hex system, as opposed to the decimal or binary system, has 16 digits. They go from 0 to 9, and then you add 6 alphabets, A, B, C, D, E, F. So you get 16. So what's the magic behind 16? It's really built, or it really represents 4 bits adequately together, and is able to get, 4 bits range is from 0 to 15, and that whole range can be represented by a single digit F in the hex system. All of 1111 is represented by F, and all numbers between 0, 0, 0, 0 and 1111 will be represented between 0 and F. So it compresses how we can show numbers. Similarly, 8 bits can be represented by 2 digits. So 255 in decimal is represented by 8 ones in binary, but in hex we can just use 2 Fs to represent 255. On the right, now you can see the mapping here between binary, decimal, hex, and another system which is octal. Now octal isn't used a lot, but I just put it out there because you are able to represent numbers in octal as well, and how these numbers, the same numbers, are written differently in each of these systems. And here's a chart of the number of bits and how large a number you can represent with those bits in decimal, which is the max number, and then the equivalent of how you can actually represent the maximum number in hex. So you can see that even for a 64-bit system with hex, pretty much we divide 64 by 4 bits because 4 bits represents 1 digit, and we are able to represent with 16 digits in the hex system. And with 64 bits, we are able to represent a really large integer, and that's like an 18 with, I don't even know what it's called. It's like a billion times billion on that number. Hexadecimal numbers are represented by adding a 0x to the left, and that's a typical notation in computer systems or when we represent these numbers. So let's get to something more interesting now with these numbers, and that is, we know the bits. Now we can do a 2-bit addition. How do we do a multi-bit addition? So you take two numbers, and how do you add them? There are two concepts fundamentally. One is the use of unsigned numbers, and the other one is the use of signed numbers. So we will go through first through unsigned numbers, and then later we will get to signed numbers. Unsigned numbers, let's take an example, 3 and adding 3 to 10. So we will represent 3 in binary here, and then we will represent 10 in binary, and then we will add those two digits together. So this is a simple case. It adds 3 and 10, and we can add each of the bits, and then we see the resulting number as 13. Let's take another example. Let us add 15 and 15 together, and both individually can be represented here, 15, and the other one, 15, can be represented. They're all ones. Now this case is interesting because when they all add up, they carry 1 to the left, and they all carry 1 to the left until the 1 flows over. Now this is called an overflow, and ultimately 15 plus 15 is not really 0. In 4 bits, you cannot actually represent a 15 plus 15 addition because you cannot represent the number 30 in 4 bits. So this indicates an overflow situation. And in computer systems, there is an overflow flag which will indicate that you had an overflow because you couldn't get the results in the number of digits that you were using to compute. Now let us get to a case of unsigned subtraction. We just did addition. So how do you subtract? The computer systems are very efficient in addition. The way they do subtraction is actually through addition. And here is a simple logic of how you get a negative number out of a positive number. you can create a 2's complement of a number to get the negative of that number. So in this case, we are doing 15 minus 7, and because in the computer logic we would rather add, we're going to add 15 plus minus 7. Now, how do you get minus 7? So the way we get minus 7 is by adding the 2's, by creating the 2's complement of 7. And how do you get a 2's complement? There are 2 steps to getting a 2's complement. You flip all the bits, which means if you have a 1, you make it a 0, you have a 0, you make it a 1. And then in the next step, you add a 1. And that creates a 2's complement. And that represents a negative of the same number. And this works both ways. If you have a minus 7, if you take a 2's complement, it becomes a plus 7. If you have a plus 7, you take a 2's complement, it becomes a minus 7. Now, so what we will do in this case is we just took the 2's complement, and on the right side, we represent the minus 7 by taking the 2's complement of the number. And now we add up these two numbers. We do an addition of 15 and minus 7, and the result you can see is an 8. Now let's see, how do we represent signed numbers in computer systems? We just did addition, we did subtraction of unsigned numbers, but how do you represent a signed number? So what we do is we use take the leftmost bit of the number and use it to represent the sign. 0 is used for positive numbers, 1 is used for negative numbers. So what happens is, if you're going to take a bit out of the number, you're only left with the n. If you had n bits to represent a number, you're left with n minus 1 to represent the number, because the nth bit is now taken to represent the sign. So if you take the 4-bit signed example and you take 1 bit out, the positive range for the 4 bits becomes 0 to 7 only, because the leftmost becomes 0 for positive numbers. The negative number range becomes from minus 8 to minus 1, because the leftmost bit, number 1, is now indicating the negative sign. So this table represents the full 4-bit spread between how you would represent a positive number and a negative number. And because we used 2's complement in the previous model, the 2's complement is still the way to calculate to get the negative numbers out of the positive numbers. So we represent the negative numbers here with the 2's complement. And these numbers, 15 in total, 0 to 15, 16 in total, are still there. But now what has happened is half of the numbers have gone to the positive range and half of the numbers have been moved to the negative range. So the total range, instead of being 0 to 15, is now minus 8 to plus 7. Now let's move to binary arithmetic and see how a signed addition will take place. So let's take a simple example. On the left side, we add 3 and 4. Both are signed, so the leftmost digit now indicates the sign, and that is 0. And now we represent both of these numbers. 3 plus 4 is 7, and that's perfectly okay. So we get a simple signed addition here. In example 2, let's try to make it a little bit more complicated. 3 plus 5. Now 8, we know, cannot be represented in the number range. So how does the addition happen here? So we add 3 and 5, and as we add up the numbers, there is a carry, and that carry eventually flips the sign bit. This causes an overflow. Addition of 2 positive numbers should not flip the sign. Neither should the sign be flipped by the addition of 2 negative numbers. So in this case, we see the overflow is set. We are really indicating that this cannot be represented here, because 3 plus 5 is not really minus 8. Let's look at some more examples of signed addition, and in this case, let's get positive and negative numbers together. So let's take another example, 3 plus minus 6. So we have represented 3 as 3, and we represent minus 6 as minus 6, which is really the 2's complement of 6. And we add up all these numbers. and it adds up perfectly fine to -3. The 1 on the significant bit represents the negative number here. Let's take another example on the right where we are adding 7 and -5. So same way we represent 7 as a positive number, -5, you can see the leftmost bit is 1. We add up these two numbers and we get a positive number 2. So this is also a perfect way to add up signed numbers. Now let's look at how we do signed subtraction. The way we do signed subtraction is exactly the same way we did signed addition. So let's try -7 and subtract -4 from -7. So the way we will subtract -4 from -7 is actually by trying to convert the subtraction into an addition. So we will take -7, and instead of subtracting -4, we will add the 2's complement of -4. So that's a negative negative. And so taking the 2's complement of -4, we know that that's represented as +4. So in this case, we take -7 as the first row, the second row becomes +4, and we add these two together. And as we see the addition, it comes out to be -3, which is perfectly what we wanted. And you're just adding up the bits lined up here together. We can take another example, and in this case, we will do a subtraction of a -4 from 7. And 7 minus -4, so what we will do is to do 7 minus -4, we will again take the 2's complement of -4 and we'll convert it into an addition. So in this case, we have on the right side 7 plus, and the -4 on the left side, we took the 2's complement, so it has become +4. Now we are going to add these two numbers. In this case, what we see is that we actually have a change here in the sign. Now the addition of two positive numbers, because we are doing an addition, cannot change the sign. And so an overflow resulted here, and what it really represents is the fact that we cannot represent the addition of 7 and 4 because the maximum range of a positive number we can represent is actually just +7. So 7 and 4 is 11. In this case, we see that we flip the bit and it's all 0, 0, 0, which technically, and there is 1 on the left, so it's a -8 actually, not an 8. And then the overflow indicates an error condition technically in this case. So that's about it. That's what we covered today. In binary arithmetic, we covered bits, then we covered how to get bits together into logical operations. We added bits together for bigger numbers. We saw how we can do unsigned arithmetic with addition and subtraction, and then we also saw how to represent signed numbers and then do basic addition and subtraction on a signed number. All right, thank you.